let's get answers to generate the 60,000 odd algebraic equations and solve them. So I'll hit solve. And you have to, highlight solution in the tree to maybe to see solve. And we get a warning. I'll get to that in a minute. So at this point, if I go back to mesh for just a moment and highlight the nodes, you don't need to do this. So the displacements at all the nodes, the 20,000 odd nodes is now known. And we can get answers to interpolate those values and plot the deformed shape. So let's get answers to do that. I'll highlight solution in the tree, deformation, total. And I'll right click, and this is post-processing. So I'll just right click and say retrieve this result. And I will click on Z for zoom to fit. And I'll manipulate things a little bit. So what I'll do is I'll say show undeformed model. And I'll say show the displacements as smooth contours. And you can even look along Z. Maybe that's more what the classic beam theory view is what is familiar. And this is, this is actually scaled down the displacement. So the true scale, that's what the displacement looks like. And this message here, if I click on it and I double click on it, the deformation is large compared to the model bounding box. Verify boundary conditions or consider turning large deflection on. So this is at the limit of where linear theory is valid, and we did do a quick check and it seemed like there is, a small difference if we bring in nonlinear effects, which is much more complicated. So that's what this warning is about, and we will live with that for this particular analysis. And the maximum displacement is 3, it's the value shown over here. Let me change the units to meters. By the way, if I want to know how to change the units, I can also, search over here and it will tell me, take me there. So you can also go to home results and change the results. I just want to show you that the quick launch is useful. And if your view gets garbled under home, just hit reset layout. Okay, so the maximum displacement is 3.2. So I can go to the table that you need to fill out, and I can say the maximum tip deflection is 3.20 meters. And you can get the corresponding analytical value from the MATLAB code, which you're not don't need to do it over for this particular case. I'll get to the comparison. Next, we want to know what is the bending stress in the phase sheet. So I'll go here. I'll highlight solution in the tree. Before that, I want to show you, you can save this image by going to Home, Images, Image 2 file. And I'll say OK, and if I go to this PC, temporary files, I'll say deformed shape, PNG. Okay, so that saves a copy of the deformed shape. So if I go to temporary files, I see that PNG file has been created. So I'll go back to mechanical. Okay, let's look at the phase sheet bending stress, which is sigma XX. So I'll highlight solution in the tree, go back to the solution context menu. I'll say stress. It's a normal stress. The bending stress is a normal stress, and it's in the x direction. And I can rename this, right click and say sigma xx for FS phase sheet. And then instead of for all bodies, I'll click here and then zoom in. And I want to select bodies. So I'll select the top one, control click, and if I need to zoom in, and control click on the bottom one. That way I can select both phase sheets, and then I'll say right click, retrieve this result, and what I'll do is I will just I'll say show elements, and I will say show me the stresses on the undeformed phase sheet. And if I zoom in, and this is a little hard to see, if I zoom in here, you see that the phase sheet stress, you can hit probe. As I move in here, the magnitude increases, moves towards the fixed edge. Let me actually change the units to millimeters. That'll give me the stress, the phase sheet stress in megapascals. And if I zoom in here, I see that I do get some edge effects, so we will ignore that here, and we will pick the value, say a couple of elements from the edge. So I can just click over there, and that'll show me that value, and then let me get the corresponding value on the bottom, and you can see that that is equal and opposite, which is what we expect. The top sheet is in compression, the bottom sheet is in tension. So I can go back here and actually enter, what was it? 151.27, that's the Mac 150. So I'll just round it off to, technical problems, 151. And this is minus 151 megapascals. The minimum is just, the most compressive value. That's how you get those values. And if you want to get rid of the labels, you can highlight label, click on the label, and delete. Similarly, we can get the shear in the core. So what I'll do is I'll say stress, shear, and the component we need is XY. And instead of all bodies, I will select the body selection filter and just select the core, apply. And then retrieve this result. And then if you go here, you can see that again you get some edge effects. So we will stay about 2 elements from the edge. And if I probe in the center, it's about 0.06 megapascals. And at the top of the core, where it meets the top phase sheet, it's again about 0.06. And you see that there's not much variation in the y direction, which is one of the assumptions in the hand calculation or the analytical result. So I can come back here and say the maximum core shear stress at midplane is 0.06, much lower than the phase sheet bending stress, and in the middle it's 0.06. So it's essentially these two values. We are ignoring the edge effects, and then as you move away from the edge, the shear stress will keep decreasing. And then to update these results for a different material, all you need to do is go back to Workbench, Engineering Data, and add, new materials. Or just to show you for illustration, if I say duplicate face sheet material 2, and I'll say duplicate core material 2, and I can go and edit these values, and then I'll go back to project, say refresh, then go back to mechanical, change core to core material 2, similarly the face sheets to face sheet material 2. I haven't changed the values here, but you'll have to change the values, and then when you hit solve, all these results will be updated, and that will be for the case where you also have the analytical solution. So you need to update these values for the different material properties that are given in the problem statement, and then compare it to the corresponding MATLAB results. And so let's not forget to go back to Workbench, File, Save, File, Archive, and overwrite that. And then go back to the folder, save the WBPZ, the PNG, and the step to your OneDrive. Files, WingSpar, and I will replace the WBPZ. Good luck. Have fun.